I wish we were in class so you could do this experiment, but in the light box, which is here, there are several different optical devices. We call them optics for short. I have a plane mirror that's set up. I have a convex mirror. Actually, that's concave. That's convex. So each side is a different shape. And then here's another concave convex mirror, but it has a different angle of curvature. And then I have some lenses. So these are mirrors, these are lenses. These reflect, these refract. So there are a lot of different kinds. You have a worksheet that shows you the different types of lenses. That's one of the files that I've attached. But in general, the way a lens is named is based on the shape of each side of it. So this is a plano convex mirror. I'm sorry, not a mirror, a lens. Plano because it has a flat side, and convex because it has a bulging or curving outside. This is a double convex lens. This is also a double convex lens, but you can see the difference in the width of them causes a different refraction of the light rays. This is a double concave lens, and these here are different shapes. These are prisms. We have an equilateral triangle lens. So three equal sides. Well, it's not three equal sides because this is, the hypotenuse is longer than any of the legs, but this is an equilateral lens. And it's not really a lens, it's a prism. And then we have a four-sided rectangular lens, rectangular optical device. So I'm going to quickly move these out of the way because I really don't want to focus on reflection so much, but I want to show you briefly what happens when we use these different triangular shapes. So I'm going to turn the light box on. We have a power supply here, and we have a light box that has I call them a slit forming device. So that makes three beams of light. The other side is a single slit. It makes only one beam of light. We're using the three slits. And if we were in lab, we could be using a 4-slit or a single wide slit. But given the status quo, or the stuff that's going on, that's not possible. This is the light box. It has a very bright bulb, and we can change this so it has a lens in there as well. But I'm going to have it set back away from the back. On the other side, it has 2 more openings, so we have a lot of different possibilities and experiments that we can do. But 2 reflective surfaces, and then this end here. So light comes out both ends. We're going to use the other light end, but that's how bright the light is. So it's really intense when we're in class. And if the bulb is burning, you need to be very careful when moving it around because that bulb is fragile. So I'm going to put the slit former in, and I'm going to turn out the lights, and we're going to just see whether we can do this or not. But first, you see the 3 distinctive beams of light. We call those rays. And I'm going to ask you to make a ray diagram in our lab with the refraction of the eye. in a few minutes. But if I align the point of this equilateral triangular lens, you can see that some of the beams are reflected as they hit a new medium. They're passing through air here, but then when they hit this new medium, this plastic, it's not really glass, but it's a very good plastic. You can see some of it is reflected and some of it is refracted. And I'm going to turn out the lights so that we can see a little better. Whoops. Whoops. Okay, so I don't know if you can see that.
Mm-hmm.
All right, and as I twist it, look at what's happening over here. We're seeing the spectrum of white light show up. Yeah, the purples, the blues, the greens, yellows, reds. So I'll quickly try these different ones, starting with the point, the center. So there again, you see the reflection happening over here, refraction happening over there. And as I rotate this, you can see the different frequencies are being bent.
It's hard for us to see any color.
Yeah, okay. Sorry about that. And here is this one. So again, the idea is when light strikes a new medium, some of the light may be reflected, but if it's a transparent medium, it can be refracted. So this is true with different temperatures, air temperatures. It's true with different water temperatures. And I think we've had enough of me doing this.
It's fun.
Okay. Anyway, I wish you guys could be doing that. I'm going to change the setup a little bit, and we're going to talk about the eye. And the eye is such an amazing organ that we have. I really hope you are taking care of your eyes, protecting them in the bright sunlight. But anyway, I've got a model of an eye. In fact, you have this in your, it's a file that I included in your materials on Google Classroom. And what I'm going to do, let's see if I can, well, let's try the plano convex and see what it does. So you can see that it obviously bends the light, which in specifically is called refraction. It's different than diffraction. But to describe some points, we have the focal point of this lens right here. It's where the focal point is where they all come together. And the focal length is the distance from the center of the lens to the focal point. So that's the focal length of a lens. But quickly, let me just show you the double convex lens. So there's the focal point there, and the focal length is seemingly short. But what if we use this double convex lens? Notice what happens. The focal point is way over here. Now that's more like the eye really needs to work. If you have 20/20 vision, that focal point is ending up right on the retina. Whereas if it's, if the focal point is ending up in front of the retina, like here, that's called, I think that you have a copy of this sheet. It looks like this, refraction in the eye. But if that is happening in front of the retina, you have myopia, or it's called nearsightedness. And here's a normal eye where a ray diagram where it shows the refraction of your lens that's in your eye and how the focal point is ending up right on the retina. Whereas here is nearsighted, but we have a way of correcting nearsighted vision issues, and that's the gift of technology that I think Newton really introduced us to the beginnings of this. But let me just show you what an optometrist would do. Is he would take a look at your eye, and he would figure out where the focal point of that eye's lens is, and then he would prescribe another lens. Now I'm going to use the double concave lens, and should I turn out the lights?
Maybe. I don't. Well, I guess. Yeah, you can still see the circles.
Okay. So I'm going to move this double concave lens closer to the eye, and notice what happens to the focal point. The focal point is brought right back on the retina. And this is where if you have where what do you call those lenses? Brenda has one.
Progressives.
No.
Oh.
You put them on your eyeball.
Yeah. Contact lens.
It's called the contact lens because it's in contact with the eyeball. Anyway, a contact lens really gives a nice fine-tuning of that focal point on the retina. But that's a double concave lens. So it would be interesting if we had time to experiment with the other lenses to see what would happen with a plano convex lens. And I can throw it in real quick. But we can see that whoa, wow, that's super nearsighted. That's not a good thing. If we reverse it, yeah, still a problem. So what I would like you to do on the sheet that looks like this diagram of the eyeball, I would like you to go ahead and take, and I know you haven't been able to do measurements because of the nature of our distance learning, but I'd like you to draw on top of the eye diagram, I'd like you to draw a double concave lens. First, first, I've got it.
There we go.
I was going to say, first I want you to draw the nearsighted problem, but I'm not going to have you do that. I'm going to have you show the corrected version, and make sure you show the proximity of this lens to the lens of the eye, and how the focal point ends up being right on the retina. And there is a lot of other stuff that's so fascinating about the eye. Look on the PowerPoint, because I think I have 2 or 3 slides about the eye and how it's designed in terms of the retina to have photoreceptors that are sensitive to specific frequencies of light, and those are cones. The cones are cells that see color or transmit the frequencies to your brain, and your brain processes those as colors. And there are also another part that's called rods, and the retina is just filled with these different rods and cones, and that allows you, the cones allow you actually to see the difference in darkness, grays, you know, like the penumbra and the umbra, different quantities of light per se, and it deciphers that in the brain, and then the cones decipher the color. Okay, so I wish we're together so we can get into more detail, but that's long enough. Hope you're having a good time.